Okay, so you should have availability week 1 folder. So these PowerPoint slides are going to be out there as well. They're in PDF files. So I'll put those out there every week prior to our meeting. So you'll have those available if you want to have those and either make notes on them or something that you'll be able to go through that. Okay, I'm going to go ahead and minimize this stuff, get it out of the way so it doesn't show up in the recording. All right, so let's go ahead and get started. This is Advanced Surveying and Construction Layout. This is CET 110. Let's get it started. For some reason all right, there we go. All right, so what we're going to be talking about today, first thing we're going to do is go through the course outline. We do have 2 sections in this class. So I'll explain that a little bit. And I did have that one typo issue on the one. I hope that got all rectified. I'm sorry about that. Hopefully that won't happen again. Then we're going to talk about what construction layouts entailing, get into some of this, measurement principles. So this will be a bit of review of the information that you had in 105. So the first week, couple weeks, actually, we're going to be dealing with a little bit of that review, but next week we'll start to get into stuff that should be different for everybody. So hopefully that'll change. We're going to look at units and unit conversion, measurement types of things that we'll get into, measurement of distance, measurement of angle, measurement of elevation. Again, all of the things that you should have covered in the 105 class, okay? So let's take a look. First off, I want to look at the syllabus course outline. So I'm going to pull one up here real quick. And if you have yours handy, you might want to pull it open as well. Let me go to mine real quick. Okay. So this is our course outline. You're either in section 900 or 901. So essentially they're going to be exactly the same. The only difference is in the lab meeting time. My name's Jim Decker. I'm going to be your instructor. Just to give you a little bit about me, I am a professional surveyor in the state of Ohio. I'm a full-time instructor at Cincinnati State. I teach actually out of 2 sections now. The Civil Engineering Technology, the CET, which I believe most of you probably are in the CET section. We also have a new surveying section, so I'm kind of in both. I've got my feet in both sections there. But I'll be your instructor for both the lab and the lecture sections on this one. And I've been here 30 years plus, and in that time I've developed a lot of the different classes. So I teach a lot of varied things. But primarily my focus is like CAD, design, and surveying. So a little bit about me. I do have contact information, so you can contact me several different ways. Email, james.decker@Cincinnati State, or that 513-569-175. That's my office number. Although currently, because the building is no longer available, the older building, because of the flood, I still don't have an office, but you can still call me at that number if you want to get a hold of me, and I'll get that message and get back with you. Also, I have posted office hours. They're all virtual this semester, but I am available Mondays from 11 to 3, and then Tuesdays, I have 2 sections of office hours in the morning before this class, 8 to 12, and then after this class, immediately after, 2 to 4. So those are also good times to contact me, and you can also go through Starfish and do that as well. Okay. So the meeting times on this course, everybody will meet on Tuesday for the lecture, 12 noon to 1:50. That'll be a virtual Zoom conference type of thing. So I'll be sending you that link out, and then we'll proceed from there. Now, if you are in section 01 or 900 rather, or 901, you're going to have different lab sections. Both labs are on Thursdays. Okay. The one lab section goes from 9 to 11:50, and the other lab section goes from 12 to 2:50. Okay, so you're either in one section or the other. Now, currently, and you might want to make a note on this, right now, we actually are going to be in 2 different rooms depending on when we're going to be doing certain things. So this was scheduled originally in room 101 ATLC in the main campus, and that'll be true once we start working on stuff outside. But for the first several weeks, we are going to be in room 152 in the main campus. That's on the old building. So this Thursday, make sure that you note that we will be meeting in room 152. I'll probably send a reminder email out to everybody tomorrow evening just to make sure that we know that, okay? And also, due to COVID restrictions and all of that kind of stuff, whenever you are in on campus doing whatever, it's important that you have a mask and you also follow the social distancing guidelines, okay? So that's going to be regulated, okay? So if we look at the required text, you can read through some of this. A lot of this just has to do with, you know, the material and that kind of stuff. I guess I should, well, we'll get to that. The required text, we are going to be utilizing this construction surveying and layout, Wesley G. Crawford. So that one is important to get. You can get it several locations, but you can get it from the bookstore. They do have it on campus, or you can rent it. Some people did that quite a bit last year. Or you can get it from Amazon. Be careful though, if you get it from Amazon or one of these other booksellers, there's different versions of this book out there. And one of them I found out last year doesn't have homework problems in it. So make sure that you get the book that has homework problems in it, because we're going to be utilizing this book for the whole semester. And so it's pretty imperative that you guys get that by next week, okay? Does anybody have any questions so far?
If we get a used book from the bookstore, it'll still have the homework problems in it, correct?
It should. The one that the bookstore has always been the correct book, okay?
Okay.
So I don't think that, but just if you're curious, just page through it. At the back of each chapter, you'll see homework problems, okay? If there's no homework problems, then it's the wrong book. That ISBN number that I have right there should be the proper number. So if you search Amazon, you can search it by ISBN number, and that should be the proper book, okay? But I had a couple students, I think it was last year, had that issue. So, I mean, it's not the end of the world. I can always run homework copies if people need it, but try to get it. It would just be better, okay? All right, so some materials that you guys are going to need. One of the things is make sure you get a calculator. We're going to be utilizing that a lot. I like some kind of scientific calculator. You can get a nice Casio one for about $10 or something, and particularly one that does angles, addition and subtraction and that kind of stuff very fluently. Those are nice. You probably want to get a notebook of some kind as well. Once we do start out into the field, which will be in about 3 weeks, make sure that you have clothing that's appropriate for the weather conditions, because we're going to be out there for, each lab is like a 3-hour lab. So you want to make sure that you have all that info.
No.
Go ahead. Questions?
No.
Okay. All right. So yeah, the labs will, when we get out there, they're 3-hour labs, and you'll be outside the majority of the time, okay? And the only thing that would stop us from going outside is rain. So cold weather or sleet or whatever, we're still gonna go out, okay? And hopefully the weather hasn't been too bad lately. You know, we've had a little bit of rain, and it'll start to warm up usually by end of February, March, something like that. So it gets to be pretty nice actually after a while. Okay. All right, so yeah, the book's the main thing. If you haven't gotten that, go ahead and try to get that as soon as possible. Especially if we're up on we'll be up on campus tomorrow, or Thursday rather. You might just jump in the bookstore and see if you can get a copy or take a look at it so that you know what to order. All right, so additional course requirements. One of the things about this is that you are required to complete labs, quizzes, and exams in order to pass the course. So you're going to have about 6 or 7 labs that you'll be doing with lab reports, those kind of things. That all has to be submitted. We'll have quizzes pretty much once a week, and then we'll have 3 or so tests. So all of that stuff has to go together for a grade. Attendance policy. You are required to take all labs. It's going to be really hard to make up a lab, by the way. And if you miss a lab, I mean, there's a possibility of making them up. It's just a matter of if that happens, you're going to have to get several students to help you, and then we're going to have to figure out a day that works. Personally, I'm available on Fridays, so I could come in on a Friday. So if you absolutely missed the lab on Thursday and can't do it, I could possibly do it on a Friday or a Wednesday, because I'll be up there as Wednesday as well. But that'll be, the burden will be on whoever misses it, okay? And you don't want to miss a lab, because that can be a big chunk of your grade. Each lab's quite a bit of points, okay? The grading scale should be typical to what you see in most colleges, 90 to 100A, 80, 89B, whatever. I'm not real sticky on the numbers. I do calculate them through Blackboard, so you'll see those numbers, and they go out to 4 decimal places. I'm usually looking for overall performance. So for instance, if you're in an 80, 88 to an 89, and you're there every day and you try hard, I'm going to be looking at probably throwing you over into the A. So I do look at overall performance. Okay, so that's important to understand. Let's look at testing and grading procedures. The exams are going to be taken in person during the lab periods, and so we'll go over that in a minute. But I have 3 tests that we're going to be taking, and so we'll be doing those in person. Those will be happening in room 152. Okay, so that's one part of the reason I secured that 152. Failure to take a test on the indicated date will result in a 0, unless, of course, you make arrangements with me. Okay, so if you make an arrangement and say, I can't do it, something's come up, or I'm sick, or whatever, COVID-related issues, certainly I'm going to work with you, and we'll get a makeup test. But basically, this is saying is if you just don't show up for the test, it's going to be a 0. Okay. Also, quizzes. I usually do quizzes once a week. I haven't decided how I'm going to do that. Probably they will occur virtually. But if they are in person, usually I don't do makeup quizzes. Okay, so if you do miss like a lab and we do a quiz, it's just not going to happen. But I think because I usually do my quizzes lectures, and lectures are usually face-to-face, I'll probably be doing those virtually. So I'll let you know about that on Thursday, how we're going to handle that. So the grading, what we're going to be getting into this semester, what you're going to have, 3 tests. They're not comprehensive. They're over the different areas that we get into. So that's kind of the good news. But the other thing is that everything we get into builds. So you just kind of keep that in mind. So there's 3 tests, 15% each. And then we have quizzes that'll be 10%. And then your labs are the bulk of that. It's 45%. And I'll be talking a lot more about labs on Thursday. So we're not going to probably delve into that too much today. But the labs are going to be, like I said, primarily outside labs, and then there'll be lab reports, and you'll be working in groups. So we do have full sections. I think we have 12 people in both both classes. So that'll put us about 3 to 4 people in a group. Okay, so we will be working that way. All right, so let's delve into this. This is really kind of the nuts and bolts, the meat of what we're going to be getting into. So what I've done is broken this down on the syllabus into a lecture content section, and then there's also a section here called lab content, and then there's a reading section as well. Okay, so let's start out with the lecture content first. And what I've done is I've broken it down by week and the date, then we have a lecture topic, and then these would be the chapters that are associated with the information. And then if there's homework associated with it, those would be handouts. So, or there are handouts, I guess I should say, excuse me. When we look at the chapter reading, all the chapter reading doesn't mean you need to read chapter 3, 4, 5, and 6 here. If you go down to that reading section, it'll show you more specifically what sections to read. So like, for instance, in chapter 3, you're really doing just pages 310 through 324, not the whole chapter. Okay. And a lot of this should be review, so hopefully it won't be a big deal. So we're going to start out just very basic type of stuff. Next week, we get into control traversing. So this is going to be a very new thing for most of you. So we're going to spend 2 weeks talking about control, week 2 and week 3, and then we're going to get into coordinate calculations. And at this point, again, that 4th week will be the week that we'll actually go out and do a traverse. It'll be either 3 or 4. We'll talk about that here in a minute. And then once we get through all of that, on the 5th week, the 5th meeting time, that we'll be doing a test. So this, instead of doing a lab, that'll be a test on that 18th. And again, that'll be, we will meet in room 152 to do that, okay, both sections. So then we start doing a lot more layout, getting into the layout section, and that's going to be the sections for week 6, 7, and 8. So we're going to do a real basic layout kind of concept. This will be a field exercise. We're going to do a building layout, and we're going to do a utility layout. And once we get through all of that, then we'll take our second test. And this second test will be based on this information up here out of week 8, 7, and 6. And then the last thing we'll be getting into is roadway type of stuff. So we'll do a roadway location horizontally and vertically on weeks 10 and 11. We'll talk about intersections, data collector use, and we may do this GPS surveying, but we may do some other things down here because I've got some, I got a person I'm working with in Messer that does all their layout. We got some ideas. We might change some of this up in chapters or weeks 13 and 14, but I'll let you know as soon as we get to that point. And then the last thing we'll be getting into would be our test, and that test will occur on the 29th, which again is our Thursday section, okay? So this is kind of like your roadmap. Let's keep this handy. This is what I work off of, and everything's here. So if you miss a week or whatever, you should know what's going on. Also on Blackboard, you will see a week that's associated with this information. And once I get next week, I'll turn on week 2. All that information will be there. Okay, so everything's going to be out there. And of course, if you have questions, you can certainly ask. All right. We go into, this is showing us our lab schedule. Now again, remember the labs will be, you'll either be in that morning section or the afternoon section. But notice the first 3 weeks, we're not even going to actually go out. So the ones that actually have the stars on them, the asterisk, those are going to be where we're going to be field exercises. So the first 3 weeks, just inside stuff. We'll go outside in the 4th week and run a control traverse. At that point, you'll be put into groups and you'll be writing a report. And I'll give you a due date for that. I don't have those scheduled yet. So I'm kind of seeing how we go. We're gonna have a basic layout lab. That'll be our second one, second report, then our building location, utility location. This roadway location, we're gonna do 2 roadway locations, the plan and the profile section. They'll both be outside labs, but there's gonna be 1 report that goes to both of those. And then we're gonna have an intersection location with our last report. Now, some of this, again, this may change down here, the data collection lab and the GPS survey lab. So it just depends on what we get into. But do note that when you do have a field exercise, make sure that you're wearing clothing appropriate to conditions. I would definitely make sure you have enough layers that you wear, and then good shoes or boots are going to be important because we're going to be out in the grass. It gets wet, it gets muddy, those kind of things. Okay. And then the reading follows up with that, and these are the sections that'll go with that. Okay. So hopefully this again is just kind of the roadmap for everybody. And again, the only difference on the 900 section and the 901 section is the lab time. Okay. Does anybody have any questions on any of that? Okay. And the rest of this is talking about other policies that you should be aware of, like no-show policies, withdrawal, okay, those kind of things. I think no-show, most of you, that doesn't pertain to anybody that's here right now, because if you show up for one class, then you've got to show. But if you don't show up within the first 2 weeks, you can be academically withdrawn from a class. So that's an issue. Also, withdrawing from a course, if you do get to the point where you want to drop a class, it's possible to do that, obviously. I think most of you probably know that, but you do basically have till quite a bit later into the semester to do it. So if you do withdraw, you don't get any money back, but it does save your GPA. So if you are failing this class and you get down to the point, it's probably a good idea to withdraw. But you can talk to me about that. Before you'd ever withdraw, I would suggest you talk to me about it and see if we can salvage your grade. I don't like anybody to withdraw for no reason. Okay, so again, the rest of this information I think is in here. You can read through that. If there's any issues, you can just let me know. Okay. All right. Okay, so if there's no questions on the syllabus, I'm going to jump back into the PowerPoint. Okay. Oops, that's the wrong one. So one of the things we're going to talk about is some measurement principles. Let's see. Oops. So we're going to talk a little bit about measurement principles, and let me check something here. Looks like something's out of whack here. Oh, okay, never mind. Well, the thing I like to start out with first, and you have this copy of this, is some definitions that you should be acquainted with, that you should have had from section, the first class in surveying. So some of the measurement principles are always going to derive back to these definitions. So you should have these definitions in the Blackboard site. But we're going to look at vertical line, horizontal line, vertical plane, level surface, and horizontal distance, horizontal angle. Okay, so I have, let me do something here real quick. If you don't have these available, they should be. You can also print this out. I have these right here. So this is out there on Blackboard, but let's just take a look at these real quick. Again, you probably already know some of these, but if you don't, then these are good ones to know. So the first one that's very important from any measurement standpoint that we get into is what's called a vertical line. So vertical line is basically, everybody should be familiar with a plumb bob. A plumb bob is a device that defines gravity. So if you just take a string and attach a heavy object to it, that string represents a vertical line. So by definition, the vertical line is the line that follows the direction of gravity at a point. So everything we do is gravity-based, essentially, in the type of surveying we're dealing with. So that's an important principle, that concept of vertical line, because everything comes back to vertical line. Okay. So at a point, if you hold a plumb bob at a particular point, there's only one vertical line that exists. The other thing about vertical lines is that they're not parallel, okay, due to the way gravity works. Let me just real quickly go over here. So if you look at this diagram, if you're on a surface like this, when you hold a plumb bob over here, it's following that direction of gravity. When I hold a plumb bob over here, it's following that direction of gravity. So technically, these are not parallel. If you're doing this in, like, say, a large building, or maybe even on a 2-acre site, for all intent and purpose, they are parallel. So the amount of deflection between these two is negligible. So most of the time, we act as if this doesn't really happen. But if you're dealing with very, very large surveys that we call geodetic surveys, because this distance is so great from here to here on the plumb bob, this deflection and what they call the verticals is very, very important. So we don't have to worry about that because we're doing what we call plane surveying. So we're keeping everything on a plane. So we're assuming that because we're on a plane, that if I put a plumb bob here and I put a plumb bob here, those lines are parallel, okay? So, but do keep in mind there is a difference, and it is important to some aspects of surveying. So from that we get what's called a horizontal plane. A horizontal plane at a point is just the plane that's perpendicular to that vertical line. So there's only one horizontal plane at a given point. So that's not the same thing as being level though, okay? So that's important to understand. But we assume basically that while we're out there working, that we're working on a horizontal plane. And a horizontal line is just a line that is in the horizontal plane or is a line that's perpendicular to the vertical line. So these kind of go together. So the vertical plane is any plane that contains the vertical line. So essentially, if you go back to my concept of my picture here, this whiteboard here represents a vertical plane because these guys are in that vertical plane. But you can also take a plane and pass it through that plane from any direction. So you can have an unlimited number of vertical planes. So that's what that's saying here, that there's for any vertical line, there's an unlimited number of vertical planes. So we'll be talking a lot about this concept of vertical and horizontal as we get into this a lot more in the next couple of weeks. So the other one is what's important, called a level surface. And this is what they call a continuous surface that is at all points perpendicular to the direction of gravity. So it actually is not level or horizontal at all. Again, we go back to this picture. This really would be an example of a level surface, because if you take another plumb bob here and you take another plumb bob here, if you throw little perpendiculars here and connect them up, you get this surface. And what's really true about the gravity surface of Earth, it's really not just real smooth, it's real bumpy because it depends on where you are. So you have certain pockets of mass, like mountain ranges will up thrust this gravity plane, and oceans will make it smaller. So it's an irregular surface. And the name that they give that surface is called the geoid surface. So when we talk about a level surface, it's a curved surface, if you will. And actually, if you've been into the ocean and you watch a ship go out in the distance, it looks like it drops off or disappears, and that's because what it's doing is it's actually following a level surface. Okay. So a horizontal distance, we'll talk a lot about this. When we do any kind of layout is based on horizontal distance. So this is the distance between 2 points that is projected into a horizontal plane. So you don't have to actually measure the distance in the horizontal plane, just so long as you project it into it. And again, we'll talk a lot about that as we start to get into the layout aspects. Almost all of distances that you see on sets of plans, though, are considered to be horizontal. It doesn't say that, but that's kind of an implied thing that's important to understand. A horizontal angle is an angle that is measured between two vertical planes. Or another way to think of this, it is the angle that's measured within the horizontal plane. So the way I think of it is, if you take a protractor and you set the protractor in the horizontal plane, when you're measuring angles with that protractor, that's what you're getting, is a horizontal angle. So most of you probably have taken that measurements class, and you know that they constantly told you have to measure, you have to level your instrument up when you turn angles. And the reason is if you don't do that, your protractor is not level, or it's not horizontal rather, so it's giving you a skewed angle. Okay? So horizontal angles will be very important. These two things together, the horizontal angle and the horizontal distance, will be used quite often together to give you what's called a position. That's very important. So then the last two types of things we have are what we call vertical angles. A vertical angle is just the angle that's measured in a vertical plane. So instead of taking your protractor, placing it in your horizontal plane, you rotate it until it's into the vertical plane. Okay, and these things are used a little bit less often, but we use them for things like slope reduction, or we use them for trigonometric leveling, those kind of things. there are two types of vertical angles. Let me just explain that real quick because that's going to be an important concept here. Let me just get a new picture here. So if you're in if this represents a vertical plane, you have what's called a vertical angle. So it has kind of like two axes that it uses. Actually, I'll try to draw that as good as I can. All right, so in a vertical angle, this is your 0 direction. And so if you go this way, that's a plus angle. And if you go this way, that's a negative angle. So what we're saying is we're looking uphill or we're looking downhill. So this would be 90 degrees and this would be 90 degrees. So in a true vertical angle, 0 is looking straight ahead, and this is also called your horizon. So this is your horizon. And 90 minus and 90 plus, this is actually the vertical line. And most modern surveying instruments don't use this technique at all. This is an old style of angle. What they use is primarily what's called the zenith angle. So the zenith angle is looks like this. If you're looking straight up along the plumb bob string into the sky, this is your zenith. If you're looking down the plumb bob string through your feet, this is called nadir. So with this system, what you have is your zenith angle is 0, horizon angle is 90 degrees, nadir is 180, this direction is 270. Okay, so it goes from 0 to 360 around. So if you're looking uphill, you're between 270 and 90. If you're looking downhill, you're going to be 90 to 270. Almost all modern surveying instruments use this technique. It's called a zenith reading technique or method. So when we get out there, start using the total stations and all those things that we'll be utilizing, this is the system that it uses. That's called your zenith type. Okay, so let's move on. Okay, so let's talk about mistakes. Okay, so mistakes occur in layout for many reasons, but one is lack of understanding of your plans. Okay, this is big because a lot of people can do layout, they can lay out distances, they can lay out angles, but if they can't look at a plan and interpret what that plan's saying to them, that's going to be very important. So that takes actually a lot of time to understand plans. Some plans are very, very simple, very simplistic, like a floor plan, for instance. There's not a lot to it. It's got mostly 90-degree angles and all your distances are pretty plainly stated. But if you looked at a set of plans for highway, it looks like spaghetti. There are so many different objects on there and lines and whatnot that if you don't know what you're doing with a set of highway plans, you better not be doing it. So that would be an example of lack of understanding of plans. Lack of knowledge of measurement techniques. Okay, this is pretty important. And this is what primarily was supposed to be developed in CET 105. That's a basic instrumentation class. So things like understanding the difference between doing a slope distance or a horizontal distance. That's what we're talking about with the measurement techniques. And then the third thing would be lack of knowledge of equipment. So if you don't know how to set up an instrument, or you don't know how to set it properly, or you don't know how to calibrate it, those kind of things, those could be all issues. So these three things kind of go together and can make or break it when you're talking about doing any kind of layout. And the other thing I should say that layout, I've done a lot of layout in my time, and layout's always high pressure. So you're usually under the wire trying to get things done because there's a heavy equipment like right on you trying to get into there. So you also have to work pretty fast. All right, so let's talk about errors. A large mistake is referred to as a blunder, okay? So if it's a small mistake, we just usually think of them as a mistake. But if they're a very large mistake, so if you've blown something by 20 feet, that's referred to as a blunder. And that usually occurs due to just carelessness or not knowing what you're doing, or again, not looking at things. So blunder is actually an engineering term. So when you hear that, it's a very, very large mistake. So you can do something like just measure a slope distance when you should have been a horizontal distance, and that can produce a mistake, but it can be a pretty small one if the slope you're on is not that much. But if you blow it, like I said, 20 feet, that's huge. So that can also be very costly to whoever makes that type of mistake. Okay, so when we look at this, how can we eliminate this stuff? How can mistakes be eliminated? So one thing is to do what's called check and recheck. So in other words, you might measure it from different directions or different locations, or you might do it what we call redundantly. So redundancy is where you're measuring things several times. One of the things we do a lot of times when we turn angles, and I'll explain this when we get out in the field, is that you'll turn the angle one time and set it, you flop the scope, go back and resight your sight, and then turn that angle again. That's what we call doubling the angle, and that's an example of redundancy. Redundancy is very, very important because if you don't do that, you don't always know you've got the right angle. I had a case where on a very tall high-rise building we were working on, some other company had set control, and it was supposed to be a 90-degree angle, and long and short of it is it turned out to be not a 90-degree angle, and we were erecting steel based on their sightings, and the building was coming apart because the angle wasn't 90 degrees. So it became a big problem. But my guess is probably they just turned the angle once and set the mark, and they didn't double it. They didn't check it. So redundancy would have caught that. Also try to use maybe 2 independent measurements. So that's saying instead of measuring the distance from one location twice, maybe measure it from one distance, from one location, and then measure a different distance from another location at the same point. And mathematically, that all should check. So we do this kind of stuff routinely, and I'm going to show you some techniques as we get out into that first lab. One of the first labs we get into, we're going to be talking about that and showing you how this works. So it's just extremely important to get a handle on that. Not to the point though you're measuring angles 16 times or something, because then of course you're taking way too much time. So you've got to be confident with what you're doing with maybe a couple of checks, but you can't just be doing things over and over and over and over again. So there is kind of a point where what we might call diminishing returns. Okay, so there are what we call errors that are associated with measurements that are different than mistakes. So mistakes are human-caused errors. There's something that we do. We read plans wrong. We don't set the instrument up over the point, those kind of things. Those are mistakes. Errors are things, they differ. An error is something that usually occurs after you've tried to throw out all of the mistakes that you could possibly have. So one thing to understand with an error is that they always exist in every measurement. You really, really can never get rid of them. So you just have to kind of live with it, the fact that you can't measure things perfectly, okay? They're typically very small, that's the good news. And they can be classified as one of 3 types of things, either what we call a natural error, a personal error, an instrumental error. Example of a natural error would be one that is caused by, let's say, weather conditions. So everybody knows if we go out with 100-foot steel tape on a day like today and measure a distance of 100 feet, it's not going to give me 100 feet, because that tape is going to be contracted due to the natural conditions of the steel and the temperature. So the inverse of that is if it was on a hot day, it would get longer. So that's an example of a natural error. Personal error is one that we cause, something we've done wrong. We read the tape wrong. We didn't set the instrument up over the point. We didn't level it. Those are personal types of errors. And then the instrumental errors would be errors that are induced into the measurement due to the instrument itself. So such as a tape a tape is calibrated by somebody, but we don't always know that it's calibrated properly. So calibration can be an issue. Those would be examples of instrumental errors. So there's two broad classifications of errors that occur, the systematic and the random. And they're a little bit different in how they operate. Let's take a look at the systematic first. Systematic errors are the types of errors that conform to mathematical and physical laws. So what this basically means is because they do, we can typically write an equation for them if we measure the thing that is creating the error, and we can determine how much that error is and whether it's a plus error or a minus error, and then we can get rid of it. So magnitude and the algebraic sign of the error will be constant or variable, but we can predict both of those, and so therefore we can get rid of it. So again, if you measure the thing that's causing the error, you can use that to apply a correction. So an example of that is the steel tape I just talked about. Steel has a coefficient of linear expansion because it's a particular material. That's a known constant. And if you measure the temperature that the tape was calibrated at and the temperature that the tape was measured with, the time of measurement, you can determine the amount of temperature change. You can write an equation for that, and then you can determine whether it's a plus error or minus error, and you can also determine what its magnitude is. So you can correct for that. So that's an example of a systematic error. And systematic errors over time, they tend to accumulate. So they're sometimes referred to as cumulative errors. So again, if you're measuring with a steel tape on a 30-degree day, every time you measure 100 feet, you got the same error. So it's just stacking up. Okay, so those are good. Those are easy errors to handle. However, if you don't understand that they're occurring and you don't measure what is causing that error, then you're going to have a problem with it too. So again, that goes back to your understanding of measurement. So the other type we have is what's called a random error. So a random error will always be in your measurement, even if you've taken all the pains to get rid of the systematic errors. It's going to remain. And the good news is they tend to be rather small, and they tend to compensate themselves out. So these are caused by factors beyond the control of the observer. They're sometimes referred to as accidental errors. They do tend to obey laws of probability. So if you're familiar with the bell-shaped curve kind of concept, you know, the actual number would be in the middle or the peak of the bell shape, and then you'll have what are on left and right of that, what we call outliers. So as you're measuring, if you measure a lot of different numbers and you graph them, what you'll usually get is that bell-shaped curve. You'll have outliers on left and right, and you'll have most of the measurements will tend to occur at the peak of it. And so a lot of people will use redundancy and then average them out. That's probably not the best way of doing things, but they do tend to practically cancel out in a series of measurements. So they're sometimes referred to as compensating. And that's why a lot of times we take several measurements and then we'll average them, because what we're doing is getting rid of those. Okay. So the two things, again, very important. Systematic, which is something that we can deal with a little bit more, and we'll investigate some of these as we get into some of these labs, and the randoms, which are just things that are there and we can't get rid of them very easily. So we have the concept of accuracy versus precision. I'm sure that you guys are familiar with this concept too, but accuracy denotes the absolute nearness of a measured quantity to the true values, which to me is somewhat of a nebulous concept, because we don't really know that always. But so it's how true or how close we get to a real number, the actual number. And precision refers to one of two things: either the degree of refinement or the consistency of a group of measurements. So what I mean by degree of refinement is if you take let's say you take a ruler, and that ruler is graduated into inches and half inches, it's not very precise, because you can't get much better than a half an inch. You can estimate it to a quarter. But if you take another ruler that is graduated to the 16th of an inch, that has a higher degree of precision, because the numbers on there are smaller, so you can guesstimate it to a 32nd. Consistency in a group of measurements is also precision. So what that's saying is if you take a steel tape and you go out and you measure a distance between 2 points and you get 100 feet and 100 feet and 100.01, 99.99 and 100, those are pretty close to each other. So that we would say has a high amount of precision. So we tend to think that measurements with small discrepancies indicate high precision, but a lot of people will think, oh, well, if it's high precision, it's high accuracy. But here would be an example. If you took that steel tape and you cut 1 foot out of it in the middle and spliced it, and then you went, I had you guys go out and measure, and you're telling me, okay, it's 100 feet, it's 100 feet, it's 99.9, you're getting all these numbers that are very close, you're going to say, oh, I got high precision, so my numbers have to be right, but actually they wouldn't be. So precision is not the same thing as accuracy. The degree of precision attainable is dependent on equipment sensitivity and observer skill. And most of the equipment we use is pretty precise now. But usually you can look at it this way: as the more expensive a piece of equipment is, usually the higher the sensitivity is, so it's going to have a better degree of precision. And also an observer has to be pretty good at turning angles and whatnot. So if they're not very good or they're getting parallax, those kind of things, that could play in and make a difference. So the key thing, though, think about this, that precision and accuracy are not the same thing, even though we very often, when we're measuring, if we get high precision, a lot of times we're going to think, okay, we're okay, so we've got to be pretty accurate. And everybody kind of uses that concept, but again, that can be a problem. That can be an issue. Okay, so units. I want to spend some time with units, and we're going to spend this lab. We're going to be talking about several things in the lab on Thursday. One of them is going to be unit conversion. I need you guys to understand this is a really, really important concept. It's not hard to do, but I just taught a statics class, and I don't know how many of you guys are taking statics or strength of materials, but I just got done teaching that. And a lot of the stuff right out of that class has to do with units, and even towards the end of the class, we were still having unit issues. So units are going to be important any type of measurement that you deal with. So we can break units down into types. One would be a length unit. We talk about angular units, area units, and volume units. So the length units, particularly for construction and construction layout types of purposes, typically are done directly. So that means when we call it direct measurement. So if I measure with a steel tape for distance, I'm actually getting a length. That's a direct measurement. If you're using some other kind of thing, like you're turning angles and calculating distances from those, that's an indirect unit of measurement, or not unit of measurement, but a indirect measurement. So for length, we typically have feet and inches, or feet, tenths, and hundredths, yards, and meters. So architects primarily work in the feet and inch world, and surveyors and layout people, very often we work in the feet, tenths, and hundredths world. So when I go to grab a steel tape out of my truck, it's graduated in feet, tenths, and hundredths. But all of my plans are going to be marked in feet and inches. So I'm going to have to do a conversion back and forth. Yards are very limitedly used. They are used maybe for some site work, particularly when you get into earth types of things like earth moving. Meters, too many people are dealing with meters. You might see some federal projects in meters. But we are primarily an imperial world, or in this country, so we don't see that too much. At one point, the Ohio Department of Transportation had a thing that they were going to go completely meters back in probably the 80s or something like that. And they actually required people to do things in meters and lay out meters. And they had a pretty major project that got screwed up because people didn't understand the conversion factors. So that they kind of completely scuttled that. So they're now back to an imperial world. So these would be length type. Then we get into angle. Angles can be done directly, but a lot of times they're also done indirectly. But they would be in one of 4 types of major categories, either degree minutes second or what we call DMS, or decimal degrees. And then you either have the grads and the radians. Grads is more of a European counterpart to the imperial system, and the radians is primarily digitally used or with computer type applications or some mechanical engineering. So you won't see any surveying type instruments or layout type instruments. They're pretty much always going to be a degree minutes second format. However, if you're working with a calculator, a lot of times when you're calculating things, sine, cosine, tangent, those kind of things, your calculator may be giving you decimal degrees. So being able to convert back and forth between degree minutes second or decimal degree, that's going to be also something that'll be very important. Again, I'm going to show you some of these things as we get into this. On Thursday, we're going to go over this quite extensively. So the next one is area. Area typically is an indirect measurement because that means you're measuring other things to actually get area. Now they do have devices now that you can set up and basically scans areas, and it can give you an area calculation, but it's probably doing it indirectly as well. But an area primarily, we call that a derived distance, so it's a value, so it's a distance times a distance. So you're going to have units of what we would call like square units, so square feet, square yards, square meters. But then you have these other 2 guys that don't have the square after them, so the acre and the hectare. The acre is the more commonly used land boundary measurement unit in the United States. We also use square miles, but primarily acres. And then hectares is the metric system unit of area. So there's about 2.5 acres per hectare, I believe, or it's vice versa. We'll see that in a minute. All right, so volume would be the last type. And again, if you're dealing with construction layout, this can be a big thing, primarily if you're dealing with earth moving off applications like roadways or parking lot, that kind of stuff. Calculating volume is important, but it's typically an indirect measurement as well. And it's a distance times a distance times a distance, or the way a lot of people calculate it is they calculate an area and they take that area and they move it through a distance. And so what they do is generate volume. So the common units there are cubic feet, cubic yards, and cubic meters. And the one that's probably the most common for construction purposes is the cubic yard. So like when you order concrete, you usually use it in cubic yards. If you're moving dirt, it's usually in cubic yards. So those, again, very important. So let's take a look at this. I'm going to give this to you. We're going to go over, I'm not going to do any calculations right now, but I'll get into this a little bit here as we get into this, but particularly on Thursday. I want to show you some key ones here to think about, though. I'm not saying that you have to memorize these, but some of these would be really, really nice to know. So in fact, some of you probably already know these things. But of course, I think everybody pretty much knows that 1 foot is 12 inches and 1 yard is 3 feet. But when you get into the metric conversions back and forth, you need to understand there's a couple of different feet out there that people don't really realize. And it also depends on where you are in the country, whether you're an international foot state or you're a US survey foot state. But there's 2 differences here. For the international foot equivalency, 1 inch is exactly equal to 2.54 centimeters. And for the US survey foot, 1 meter is exactly 39.37 inches. So the reason that came about, because in the late 50s, early 60s, they came together and they wanted to come up with an actual standard physical or a constant that was a different constant than they had for the meter. And so they used a wavelength of orange krypton gas in a vacuum to determine that. Well, what that did was that came very close to the original. This was the original number. This 1 meter is 3937, but it wasn't exact. So they kind of developed 2 different feet systems. And for surveyors, people practicing, this is important. So depending on what state you're in, you're either using this equivalency or, whoops, let's go back. You're either using the international or the U.S. survey foot. So just to give you an example, most of the states are U.S. survey feet states, but a couple of them aren't. Ohio is a U.S. survey foot. Indiana and Kentucky, I believe they're all U.S. survey foot, but Michigan is not. Michigan is international feet. So if you're using a total station and your total station is set to U.S. survey feet and you're in Michigan, you're going to have mistakes when you start measuring stuff. Now, they're small, they're parts per million, but when you start shooting those distances out miles, then it starts to make a difference. So we'll talk about that a lot more as we get into this on Thursday. So some other surveying units you may or may not have heard of: the rod. These are old English terms: the rod, the pole, the perch. You can go down to the courthouse here in Ohio, Hamilton County or Kentucky and find these units on old deeds. But the rod, the perch, and the pole, they're all 16.5 feet. And we also had this other unit that was a common unit in measurement for land, which was called the Gunther's chain, 66 feet, which was broken down into 100 links. And notice it was a quarter of a chain is one rod, pole or perch. So 4 rods is equal. So these are all old units of measure. And we have the mile, 5,280, and that's going to be equal to 80 Gunther's chains. And of course, then we have the kilometer and the 1,000 meters. So for layout purposes, you're pretty much going to be using either the foot and the inch or the yard, and you might be going back and forth between meters and stuff. So that'll be important. We'll talk a little bit more about that again on Thursday. And then angle, these are some common factors. So 1 circumference or 1 revolution is 360, and then you got 1 degree is 60 and 1 minute is 60. So this is referred to as your sexagesimal system. Notice grads are a little different. You have 400 grads per 360 degrees. So this system's a little different. This would be the European counterpart to what we use. Then you have 2 pi radians is 360, or pi radians is 180. And then you have 1 radian is exactly equal. Well, it's not exactly because this floats a little bit. Then there's another one called mils. Some people, I believe, in the military use this. So this is your equivalency. So we'll be working with some of this on Thursday. And then here's some area conversion factors. Now, if you're dealing with land boundary, this is primarily showing you some of that, like the acre is 43,560 square feet. It's approximately like 208 by 208 on a side. So it's actually, acres aren't as big as you might think when you really get out there. So you have 10 square chains is equal to 1 acre. You have 1 square mile, 640 acres. But I do want you to notice there's equivalencies for the square yard and the square feet. So 1 square yard is 9 square feet. And here's your hectare to acre equivalency. So 2.47. I usually use about 2.5 just as a rough to give you an idea between the hec and the acre. And here's your conversion factors for volume. And this is an important one too. A lot of people screw this one up. The cubic yard is 27 cubic feet. A lot of people think 9 because cubed, 3 cubed, but that's not correct. Okay, so we're going to spend more time with this. We need to think about this, and I'll get into this on Thursday. So I'm going to show you how to do some of these calculations so that we can spend more time talking about other things today. And we'll talk about this on Thursday. So let's talk about 2 concepts that we're going to be getting into. One is measurement and the other one is layout. So they don't mean the same thing. A lot of people kind of use them interchangeably or don't even think about the fact that they're different. But when we measure something, what we're doing is we're determining an unknown value between 2 fixed points. And when we layout's different. We are going to determine or set a point from a fixed point and a known value. So if I jump over, let me get over here, I'll show you what I mean by that. This is kind of we're going to be doing both things actually. And it's kind of important to understand the difference between the two. Well, very important actually. So let me just do a real quick new one. So let's say, oops, I didn't want to save it. Okay, so if we're doing a measurement, what we're saying with measurement is if you have out in the ground, you have a fixed point here, and you have another fixed point here. When you determine the distance between these two guys, so you lay a steel tape from 1 to 1, that's what we call measurement. Okay, so these guys, understand, are both fixed in the ground, and what you got going on is you want to determine what that distance is between them. Or if you had 3 points, you could do an angle. So if I had one here, and I had one here, and I had one here, I could determine the angle. So that would be an example of measurement. So if we do layout, layout says that we typically have one fixed point, okay, and we need to go out a certain distance. So let's say we go 500 feet, and we need to set this point at 500 feet out. So this is an example of layout. So you have a fixed point, you have a known distance, you pretty much also probably have a known direction, and we want to set this. We want to set this point. This point doesn't exist. So the difference here is that point doesn't exist, or in this case, that distance doesn't exist. So those are examples of layout versus measurement. And we're going to be doing both of these kind of things. Now, this course is called Advanced Surveying and Construction Layout. So it would imply that you're going to be doing this a whole lot more, which is typically true. But you do a bit of both, actually, as you get into this. Okay? So those are just some things to think about. Let's go back to this. Okay, so we're going to talk about some things. Now, I know I'm going a bit fast here, but do understand that this should be, a lot of this should be review. And so, again, we're going to take some more time to talk about this on Thursday. Now, when we get into next week's material, it's going to be a lot different. So, something that most of you have probably not experienced. So, we'll tend to not probably work quite as quickly. But I've got a lot to go through, so I just want to make sure that we're set on this. Okay. So there's types of measurement that we're going to be talking about, whether it's measurement or layout. So you can use that term, even though it says types of measurement, you can think, well, I'm either talking about layout or I'm talking about measurement. So the first one is distance, and distance can be performed one of several ways. You could use a steel tape, you could use an EDM, that should say EDM, not EMD, and total station. Most people don't even have EDMs anymore. This tool is really not there anymore. It's been incorporated actually into the total station. So used to be back in the older days, when I say 70s, 80s, a lot of people had an instrument called a theodolite, which would measure angles, but it wouldn't give you distance. So you either had to use a steel tape and a theodolite, or you could get this unit called an EDM that would sit on top of your tripod, and it could shoot the distances separately. So that was a lot harder process. But these would be the primary methods. And from a layout standpoint, nowadays, most people are using the total station. So if you're using shorter distances, though, one thing is true is that the taping is much better. So if you're less than 100 feet, you can probably steel tape the distance quicker and better than you can using a total station with a laser. Okay, so angle would be the other type of measurement we're going to be employing. And the older style method was with transit. Those things were just horrendous, and nobody uses those anymore. And there might be a few builders that use them, like house builders that still use them, but most people don't. It's pretty much of an older type of thing. The theodolite was the European counterpart to the transit. These guys were much better than these, because these guys had steel plates that were graduated like protractors. They were really hard to read. Theodolites used etched glass. They were more precise. They were much better. So these essentially, the things that both of these do, and the only thing they do is turn angles. So you can either get a horizontal angle, an angle in the horizontal plane, or you can get a vertical angle. That's all either of these guys do. So again, when they took the EDM and they put it inside of a theodolite, what they got was what's called a total station. And the other thing they did was they added computers into it, onboard microprocessors. So total station really has computer capabilities in it. It has the angle capability, and it has the distance measurement capability. So these guys, these are probably what most people are going to be using out there if they're turning angles, because it gives you the best of both things. I can get distance from it. I can also get angle from it. Elevation, the primary methods of using elevation is either using a tool called a level, or you can use a total station. But if you're doing a total station, you're doing what's called a trigonometric leveling process, which is actually doing an indirect measurement of elevation. Levels come in several different types. We'll talk about one is what's called the automatic level, then you have the laser levels. Okay? But these are actually physically, this tool is actually measuring elevation more or less, where a total station is not. It's doing other things. Yeah? All right, so let's take a look at distance. We're gonna talk about distance a bit, and we're gonna go into each of the three areas and talk about those and how those come into play, and then that should take care of today's lecture. So again, this should hopefully is a little bit of review. So when we talk about distance, there are primarily three distances that you can talk about. You can talk about a slope distance, a horizontal distance, or a vertical distance. Again, so let me just kind of give you a little slope angle that we can look at and show you this concept real quick here. Let's see if I can do this. All right, so if I assume I have a triangle here, and this is, let's say, the horizontal plane, and this line represents the vertical plane, and this would be a skewed plane, okay? And if this is truly horizontal and vertical, we should have a right angle right here. Whoops. We should have a right angle right here, which says that this is 90 degrees. So if we're measuring this distance, this would be our horizontal distance. If we're measuring this distance from point to point, this is your vertical distance. And if you're measuring this distance, this is your slope. So it's very important to understand, particularly between these two measurements here, because a lot of times people are measuring slope and they think they're doing horizontal. Particularly, I'm going to show you guys when we get out in the field, a lot of you guys will do slope distances right away, and we really are referring to horizontal, or we need horizontal. So primarily for layout purposes, these are going to be more important. These are the two that we're really after, but sometimes it's more convenient to do a slope. So if you measure the slope distance, you can convert that slope to a horizontal, or you can convert it to a vertical. If you do something like measure this angle here, by measuring that angle, I can take that slope and convert it to a horizontal, or I can convert it to a vertical. And that can be more convenient sometimes than doing that one or that one. But primarily, these are the kind we're looking at, the horizontal and the vertical. That's what your sets of plans primarily tell you. Okay. So we would have, for distance measurement, two primary methods or techniques of measuring distance, particularly for construction layout. You're either going to be using steel taping, sometimes referred to as chaining, because in the old days of surveying, you actually used chains. That's where it got that term. The other method is electronic distance measurement, the EDM. But remember, this guy is built into the total station. So you're primarily using a total station. So let's take a look at steel taping, because we are going to do a little bit of both. And as I mentioned before, a lot of people that do measurements, they'll do a 10-foot distance with an EDM, and it's for one, it takes them twice as long. And if you would just use a steel tape, you can get the distance quicker. But if you're doing distances of any great length, you have to take a lot more skill. Sure, did you guys, I would assume, measure down those hills when you did a taping exercise in 105, and you know it's a big deal to measure with a steel tape, particularly to get any kind of precision or accuracy. But the equipment that we use primarily is going to be a Cervera's 100-foot steel tape. And again, those are graduated in tenths and hundredths of a foot. So a hundredth of a foot is not a high degree of precision. It's approximately an eighth of an inch. So if you go to a builder's rule, you might see that ruler or that tape measure in 30 seconds of an inch, which is actually a finer degree of precision. But steel tapes are usually better because it's a better material that they use. We typically use 2 plumb bobs, one at each end, for particularly keeping that thing into a horizontal plane. We use a tension handle. Tension handle is to make sure that you're applying a proper amount of tension, which, depending on the steel tape and its cross section, most people say it's anywhere from about 12 to 20 pounds of pull. Doesn't sound like much, but if you guys are both, if 2 people are taping a distance and you're both up in the air, pulling with 15 pounds of tension is a lot. You need a hand level. The hand level is a little device that'll allow you to keep that tape in a horizontal plane. A thermometer would be useful if you're doing taping on most days, so that you can get the temperature, so you can apply temperature correction. And we use tacks or chaining pins if we're going any distance. So those are your primary pieces of equipment when you're doing steel taping. So steel taping requires, on a horizontal distance, you have to have a good horizontal alignment. You have to have good vertical alignment, proper tension, and proper plumbing. So again, all of those 4 things have to go together to get a good distance. And it's very hard. I know that, like I said, all of you guys have done this, so you do understand what I'm talking about. But we're going to do a bit of steel taping, but we're not going to do like anything long distances. So we're going to keep our steel taping down to a minimum distance. And when we do that, a lot of this stuff isn't as important. So tension, you don't have to worry about tension as much in a shorter distance, those kind of things. So there's many errors associated with steel taping, and we're going to investigate some of those on one of the labs, but we're going to get into a few things here, just talk about them. I'm not going to get into them in too much in depth, but one of the big errors associated with steel taping is what they call incorrect length. So what this means is that your tape is calibrated to say it's 100 feet, but it's actually not 100 feet. One thing that most people don't realize is when you buy a steel tape from a manufacturer, it's implied that it's 100 feet, but it's not exact. So you can have it calibrated by the federal government, the Bureau of Weights and Measurement, but that costs you an extra amount to have that done. But if your tape is longer or shorter than it should be, every time you're measuring 100 feet, you got a systematic error in there. So that's one type of error. Another type of error is distance or temperature that we talked about, temperature other than standard. A third one would be one that we would call incorrect pull. So if you're pulling not enough, your tape is sagging a lot. And if you're pulling too much, it's actually stretching. You have a fourth error there called sag. We're going to talk about these a little bit more in about the 6th week. So I'm going to go in depth on these a little bit and show you how to calculate some of these. But I just want you to start thinking about some of those things. So the EDM measurement requires a different set of equipment. If you have a total station, then you would just use the total station. It would have what's called a tripod and a tribrac. The tribrac is the device that actually screws into the tripod, and that can be unconnected, and the tribrac can stay there, and the total station can be lifted separate from it. You have a reflector, also referred to as a prism, which is really, it is really just a prism, typically of glass, very pure optical glass. And that usually sits on a plumbing pole with a level vial. That's not the best way of doing it. It's better to probably put it on a tribrac with a tripod as well. Because if you're just using a plumbing pole with a level vial, you get a little bit of movement, those kind of things, but we'll tend to use the plumbing pole. Thermometer and a barometer, these are used to determine what's called a parts per million correction. Parts per million has to do with the atmospheric correction. So when you're shooting your light through the air is slowing that beam down, so it tends to change the velocity, and what that does is it doesn't give you the exact number. It's pretty small, it's a parts per million. A lot of people don't deal with it, which they should. I'll talk a little bit more about that as we get out there. But you need all this equipment typically. Now, if you didn't have the total station, you had the old setup I was talking about, you would typically use a theodolite to measure an angle, and then you would set your EDM either on top of the theodolite or it would set up separately and you would shoot the distance. So the total station is so much more convenient because it does everything for you now. So the electronic distance, a couple things to understand about it. When you're measuring with an EDM, it always yields a slope distance. So it's never going to give you a horizontal or a vertical distance. And because of that, if you want a horizontal distance, you're going to need to measure either the vertical angle or the zenith angle. And remember, by today's standards, most instruments are using a zenith angle as opposed to a vertical angle. So by taking that zenith angle, then you can calculate the horizontal based on that slope distance. There are obviously many advantages over steel taping. One is the convenience and the ease that you can do it. If you have to measure 600 feet across a field with a steel tape, you're going to have a minimum of 6 times. You're going to have to do all that plumbing and tension and all that stuff. And by the time you get out 600 feet, you probably are not going to be exactly 600 feet. With an EDM, it's going to be a lot quicker, probably a lot more precise. So it just really has changed the whole dynamic on how we do distances. But back in the days before the EDMs came in, everything was steel taped, and so that was a game changer when the EDMs came in. And probably to the average surveyor, we didn't really start seeing them until the early 70s, late 1960s even. So you know, everybody was steel taping prior to that point. Do keep in mind though, I'd say for distances under 50 feet, even sometimes an EDM is not going to be as quick, nor is it going to be as good. There are errors associated with that distance in an EDM, even though they're small. It's probably better not to do it. And like I said, 25 feet, you can steel tape it 5 times quicker. So some of the errors associated with EDMs, we'll talk about those a lot more too as we get into this. But one of the things is that temperature, as I said, temperature and barometric pressure does come into play. That's called a systematic error, or what's a systematic error? But it's a natural error that creates a parts per million. So it is small, but it does affect the beam itself. Setting up your total station over a point and having it level is important, as well as setting your reflector up over a point and having it level. Because if either one of those aren't level or over the point, you're going to get a different distance. So that would be another example. Another type of error is called a parts per million correction, or a reflector constant. So a reflector constant is set so that when the EDM hits the reflector, it's either offset by 30 millimeters or one way or the other. So in your instrument, you usually tell it how much your reflector constant is, and then it calculates the distance based on that. If you have the wrong reflector constant in, every time you measure that distance, you're going to either be plus or minus 30 millimeters. So that can be a huge problem. Now, in longer distances, 30 millimeters is not that big. but in shorter distances, 30 millimeters is more important. So that's what we call a reflector constant. I'll show you some of this stuff as we get out into the field as well, but those are important things. The other one is the instrument itself, an instrumental error. It has what's called a parts per million correction and a constant error. So when you buy an EDM, it'll have two values of error that are associated with it. And those are going to be things that are important to look at. Okay, so when we're measuring with an EDM, keep in mind that we said that every time you measure a distance, it's actually giving you a slope distance, not a horizontal distance. And our primarily type of layout that we do is a horizontal type of distance. So in the older days when you were using a total station and a theodolite, or rather before the total station, you're using a theodolite and an EDM, you would have to measure both the slope angle and the slope distance to calculate it. So notice that if you're using the vertical type of angle, what you're getting is a slope distance times the cosine gives you the horizontal distance. And if you're using a zenith reading instrument, you're using a sine relationship. And again, I'll show you why this is. Some of you might be thinking that doesn't seem right, but if we look at a diagram here, let me just clean this up real quick. So if I have my instrument set up at a point here, and my reflector is sitting up here, if you're measuring this distance, this is your slope. If you have a zenith reading instrument, this is your zenith, this is 0. So what it's doing is it's measuring this angle. This is your zenith. If you want this horizontal distance here, what we're saying is that horizontal distance is going to be equal to that slope distance times the sine of that zenith angle. Okay. If you were measuring the horizontal, the vertical angle, this is your 0, this is your theta angle, and so then it becomes a cosine relationship. Slope times the cosine of theta. So they are slightly different. And notice that if we measure one angle, we can convert it very simply. So the zenith angle is always going to be equal to 90 minus the vertical angle. Now the beauty of the newer instruments, the total stations, you don't have to do any of this. They do it for you. Because the total station measures the slope angle or the slope distance. It also measures the zenith angle, and it automatically calculates this because it has an onboard processor that'll take the sine of that. So it'll spit out this distance for you. You can see the slope distance if you want to, but it usually gives you that directly. So there's many advantages to using now the total station because we don't have to do any of that math. The first total station, we had one of the first in the city back, when they first came out. And when they first came out, they didn't calculate this for you. It only shot this and it shot this. So we still thought it was a lot better because all we had to do was measure that angle and we just pull out your calculator and you could do this equation. It was real simple. But the newer ones, back right away, they brought out the processors on it and they changed that. So it's much better now. Okay, so let's take a look at angle measurement. So angle measurement really falls into one of two classifications. Either the horizontal type of angle or the vertical type of angle. So horizontal angle measurement is primarily going to be used for position. And that's going to, by and large, be what you're going to be doing the most in this class. We're going to be primarily using horizontal, either measurement or turning angles, one of the two. And vertical is used for things like trigonometric leveling when you're talking about elevation or other things, or like we just saw, slope reduction. So it is used a bit for those kind of things. But we tend to use the horizontal more than the vertical. And what's happening a lot of times is the vertical is actually going on behind the scenes and we're not seeing it. So we have the vertical angle as well. So when we talk about directions, directions are a big thing we're going to talk about on Thursday as well, because that's an important concept. But the directions are based on either what we call bearing type nomenclature or azimuths. And they're essentially the same thing, but one thing to understand is a bearing is a horizontal angle, okay? So a bearing is never a vertical type of angle, it's always horizontal. So some of you probably remember doing bearings in 105. We're going to be doing a lot of that. So I'm going to spend a good chunk of the class on Thursday going over this stuff too. So we're going to cover a lot of this again, okay? There's going to be a lot of different types of errors associated with angles, but before we do that, let me see something. I'm going to check something out here. Yeah, I forgot. Yeah, okay, I got that in there. Okay. So there's also errors associated with angle measurement, and they're kind of similar to some of the things we've already talked about. One of the big things on angle measurement is not having the instrument set up over the point and not being level. So if you have both things occurring, that's an issue, or if you have one or the other occurring, that's still an issue. So that's a big deal. When you sight your, what they call the back sight, and you sight your foresight, if you're not exactly on either of those marks, that's going to be an issue. So we have some things associated with that. Again, primarily the biggest thing is leveling it, leveling that instrument up and being over the point. That's one of your biggest errors. There's some other ones we'll talk about, but primarily those are the big ones. Okay, so if we're doing angle measurement, you can either do it directly or indirectly. Direct measurement means you're typically using an instrument to measure an angle. Instruments that will measure angles will be things as total stations, theodolites, protractors. Those are direct measurement tools. Indirect measurement is typically what you're doing is you're measuring distances, and from those distances, if you measure a series of distances, you can get angles, you can determine them through a calculation. So that's why it's saying you're indirectly measuring the angle through a distance. If you're doing a typical angle measurement, you're using a total station, a theodolite, tripod, tribrac, reflector, plus prism pole, or you might be a plumb bob, one of those things. If you want really good angles, you shouldn't be using plumb bobs, rings. What you should be using is two fixed sights, a fixed back sight, tripod, tribrac and reflector, to another fixed sight, tripod, tribrac and reflector. Okay, so let's take a look at some horizontal angles a little bit. There's a couple of different types out there. Some of them are just semantically termed, but there are two big ones that are important. One is what we call the interior angle, and the other one is what we call the deflection angle. So in an interior angle, and we're going to be talking about this next week quite a bit, the interior angle exists within a closed polygon, okay? And in this, the angles are either turned left or right. So we can't talk about interior angles if we don't have a closed figure. So let me draw a picture here. So if we have a closed polygon, such as this, what we're saying is we're going to occupy each vertex. This would be considered a vertex of that polygon. And you're going to turn an angle, and I could turn it this way, and I could turn it this way, okay? And I can turn it that way. Notice I'm turning them all the same direction. That's pretty important. There's nothing that says you have to, but if you don't, then you screw people up in the field. So a lot of people turn what we call angles to the right. These are indicating angles to the right. So these are called interior angles. So if you have a figure like this, which is not a closed polygon, notice, okay, those aren't considered interior angles because I don't know whether I'm interior or exterior. So there's a big advantage to using this type of angle. And the one is that when you do this, you can get yourself a check on your angles. So we have this thing called the theoretical summation, and that's what this sigma refers to, theoretical summation. What this says is that the sum of all interior angles have to always equal to this theoretical sum based on the number of sides. So what this says is if I have a three-sided figure where n is 3, 3 minus 1 times 180 tells me that those three angles have to sum up to 180. If I have 4 sides, 4 minus 2 times 180, that'll tell me what I get. So each, as I go up in number, I'll get a different theoretical sum. But if I go out to that figure that I just showed you and I add my angles and they don't equal to the theoretical sum, that tells me I have a problem. Either I blew an angle, one angle, or I blew several angles, or they all have a little bit of error in them. So this is a real important principle. So that theoretical sum, summation, n minus 2 times 180. The other thing is too, when you're measuring angles, a lot of people will use this concept of what they call the interior and the exterior angle as a check. So when I go to, let's see, my diagram here, first of all, since I have 4 angles here, I would take that and it would tell me that regardless of the shape of this, if I have 4 angles, it has to be 360. But while I'm out there measuring, if I want to check this angle, what I can do is measure that angle, and then I can measure this angle. And so if this is the interior angle, and this is the exterior angle, if I take the interior plus the exterior angle, they should theoretically equal exactly 360. So that's a good kind of check that some people use. Some people also call this closing the horizon. I've heard that used before. So we use this concept quite a bit, and we use that concept of interior angles, and we're going to see that pretty exclusively next week as we get into talking about control. So the other type that is commonly used is this thing called a deflection angle, and this can be used with an open or a closed polygon, but it's kind of weird because the definition of it is that you're measuring the angle from the prolongation of the backside. And I'll show you what that means here in a diagram, but keep in mind a couple of things. Is that the angle is usually defined with what we use, the delta symbol. And the angle can only be between 0 and 180, but you can turn it left or right. So again, if we go to my picture here, we'll draw a quick picture of a concept of deflection angles. So what this says is if I have a line progressing like this, now this isn't a closed figure, but it doesn't have to be in this type of angle. So if I'm starting here at point 1 and then going to point 2 and then to 3 and 4 and 5, I set my instrument up here and I backsight this and I set zeros on my scope and then I flop my scope in the cradle. What that does is it turns 180 essentially, but it's still reading 0. So I'm turning my angle off the prolongation of the backside. So this would be what we would call delta. We'll call that angle delta 2. When we get here, we do the same thing. We backsight, we flop, we go this way. This is delta 3. Then we get here, we backsight, and we go delta. This is delta 4. So notice some of the angles are going to the left. This one's going to the right, left, right. So this would typically be considered a plus angle. This would be considered a negative. That would be a plus. These types of angles, this is called a deflection angle. And these types of angles are not used that much for, like, say, buildings or those kind of things. But when you get into highways and pipelines and those kind of things, this type of angle is used quite a bit. So notice also, we can never talk about an angle greater than 180. And if we're turning it to the right, that's typically positive, left is negative. Interestingly enough, and I'll show you this when we get to next week probably, the theoretical summation of a closed polygon with this type of angle is always going to be 360, no matter how many sides you have. With this type of angle, as n increases, this number will increase. With this type of angle, no matter how many sides, whether 3 or 10,000, you should always get 360 degrees. Okay. And that has to do with the positiveness and the negativeness of those angles. Okay, so vertical angles, we talked about that a bit. Vertical angle is typically measured off of the horizon. The horizon is considered to be 0. If you're inclining off of the horizon, that's a plus angle. If you're declining or going downhill, it's a negative. And the vertical angle can only go between 0 and plus 90 for uphill and 0 and negative 90 for downhill. The zenith angle, as we said before, is or your vertical angle is straight up, and you're measuring the angle off of the zenith. You're going zenith is 0, horizon is either at 90 or 270, and nadir is 180. That would be between your legs at the 180. So again, the zenith is the type of angle that we use most often. I don't think you're ever going to see this type of angle anymore. Sometimes I refer to that as a horizon angle. Again, that's an older style angle that was based on the older types of instruments. So it's not one that you're going to see too often. Okay, directions. All right, so let's just go through these. Again, this should hopefully be a review, but we're going to talk a lot about this on Thursday as well. So directions come in one of two formats, either bearings or azimuths. Note that they are horizontal angles, okay? But they're used for giving you a direction and location. Bearings have what are called two reference meridians. The angles can be turned clockwise or counterclockwise. You have 4 quadrants, and the angles can only be between 0 and 90. So let's draw a little diagram to show you what we're talking about here. And again, I'm hoping that this is a review. If it's not, then we'll pick up with it more. Okay, so for a bearing, we assume that we have 2 reference meridians. Okay, so this is north, and we're saying that that's 0 degrees, and this is south, and that's 0 degrees. And then we have these guys here. This is east, and this is west. And east is exactly 90 degrees, and west is exactly 90 degrees. So it's impossible for any angle to be greater than 90. So a way of saying that is that your theta angle can be between 0 and 90 degrees. So you'll never see a bearing angle that will exceed 90 degrees. Now, it can turn either clockwise or counterclockwise. So if I have a line right here, what I'm doing is I'm measuring this angle like this. Let's say that's 78 degrees, okay? The problem with just saying 78 degrees is that 78 degrees can occur here, it can occur here, here, or here. So to qualify that, we break this thing down into 4 quadrants. So this is referred to as your northeast quadrant, southeast quadrant, southwest quadrant, and northwest quadrant. So now we would call this bearing north, 78 degrees east. The other thing is we can do is if we extend this line into this quadrant as a straight line, notice that the angle here and the angle here are the same. So by alternate interior angles. So what we're saying is that a northeast bearing is equal to a southwest bearing, but they're traveling in what we call opposite sense or opposite direction. So they're 180 apart in terms of the way they're facing, but there actually is, it's just a straight line, okay? So this would be called the forward bearing. This is referred to as the back bearing, okay? Now, we're gonna deal with some calculations associated with bearings. That's a pretty important concept for any layout person to understand, which we'll be utilizing. So we'll see how that works. Again, I'm gonna spend a lot of time on Thursday with this. The other type of direction angle that you're going to see there is called an azimuth. Azimuth is different in the fact that it only has 1 reference meridian. They typically use north, so that means that's 0. And the angles typically, you either go clockwise or counterclockwise, but the angle can go from 0 to 360. So again, if we look at the azimuth type of angle, when we see this, the azimuth is kind of like the bearing, except it doesn't have quadrants. It has 1 reference meridian, north, typically, And we really don't even think about quadrants, but we just measure the angle this way, and that's a plus. So east would technically be 90 degrees. This is going to be 180. That would be due south. Due west would be 270. It's kind of like the zenith system in that respect. Okay. So we don't have quadrants in this system. We can turn azimuths this way, but we would consider those negative. Most people don't do that. You'll never see me do that. So we only use an azimuth going positive this direction. Okay. One of the big things that we'll be getting into is taking an azimuth and converting it to a bearing, or taking a bearing and converting it to an azimuth, because you'll find as we get into some of these calculations that working in azimuths is a lot easier method than working in bearings. So we'll go through that again. Hopefully this has been reviewed for some of you. Okay, let's go back here. Okay, so the typical problems, and we'll talk about this again on Thursday, is converting a bearing to an azimuth, or converting an azimuth to a bearing, and being able to determine an angle between two directions. So if you're given a bearing on one line and you're given a bearing on another, you can determine what the angle between those two are going to be, because if you're using a total station or some kind of angle device, a turning device, it's not going to measure out in bearings. So you can do that kind of stuff, or you can determine a direction from a known direction and a known horizontal angle. So these are typical problems. We're going to take a look at these on Thursday. We're not going to get into that today yet. I know we're doing a lot, but like I said, this is just kind of a review, hopefully. Okay. So let's take a look at elevations, and then that should wrap us up here soon. And then I will get this thing recorded and posted for you. Okay. So the vertical distance, elevation is a vertical distance. And what we mean by that is the distance above or below what we call a datum. So if we think about a datum is just a reference. So you could have a location in the floor, and you could say that floor is my datum. And if I want to know what the ceiling is, I have to measure it based on what that location is on my floor. The other type of datum that we use very often is what's called mean sea level. You've probably heard that term before. That's not too much used in construction, because we don't typically care where the sea level value is, but we do care where we are in relation to the invert of a sewer, or where a water tap is, or where the road is. So those elevations may be more relative. There's three primary types of leveling: steel taping, which is chaining, using a steel tape and just holding it vertical, or differential leveling, or trigonometric leveling. They all have their virtues. Probably the best type of leveling is differential, because it's truly giving you a good measurement. It's quick, it's easy, and it does yield very good results. Steel taping is direct. It's nice. What you have to do is, though, make sure that you're holding that steel tape along the vertical line. This is a nice way of getting an elevation into a building, let's say from ground level up, like say 10 floors. Instead of doing multiple setups up a stairway, if you can just drop a steel tape down columns, and you can just tape along the column, that's a really quick way of doing it, and it's a really good way of doing it. But it's not going to be used quite as much as we're going to see. So differential leveling is a very direct method, and what you're doing is you're reading direct vertical distance on a level rod. And again, you guys have done this before, but we're going to be doing this a lot, so hopefully we'll get to those points as we get into them. Differential leveling techniques, there's three primary types of things we call running a loop or line of levels, profile leveling, or three-wire leveling. A loop or run of levels is usually, a loop is where you start at one point, end at the same point. A line of levels is where you go from one point to another point. Profile leveling is a method where you're not setting up the level quite as much. I'll talk a little bit more about this because we're running out of time here, so I'm going to just kind of come back to this. And then three-wire leveling is a technique that gives you redundant measurements that allows you to get a really, really good reading on your rod and not make mistakes. So this is if you're doing any kind of leveling for any kind of control, 3-wire leveling is the way to go. Let me see what time it is. Okay, probably we're getting to about time. So this is probably a really good spot to stop. So let me go ahead and stop here and see if there's any questions. I'm going to go ahead and pause the recording.